In the fall of 1996, inside a crowded lecture hall at a public college in the Midwest, Professor Daniel Harper walked to the front of the room with nothing but a piece of chalk. He had a quiet confidence that came from decades of teaching. The students in calculus I had heard rumors about him. Some said he could solve any problem without looking at notes. Others said he cared more about understanding than speed. That morning, he wrote a single expression on the board. Lim as x approaches 2 of x for divided by x2. Then he turned around and asked, "What happens if we plug in 2? A few students answered, 0/0. He nodded. "And what does that mean?" Silence. He explained that 0/0 is called an indeterminate form, not because it has no answer, but because it forces us to look deeper. He factored the numerator into x to x plus 2, carefully canceled the common term, and rewrote the limit as x plus 2 as x approaches 2. When he substituted again, the answer appeared 4. The tension in the room eased. What looked impossible a moment earlier had unfolded into something simple through algebraic insight. But Harper did not stop there. He erased the board and drew a curve, smooth and rising. Limits, he said, are about approaching, not touching. He described how early mathematicians struggled with motion and change. How the idea of getting infinitely close without arriving challenged intuition for centuries. Then he introduced the derivative from first principles. He wrote the definition, the limit as h approaches 0 of fx plus h minus fx, divided by h. He chose a familiar function, fx equals x squared. Step by step, he expanded x plus h squared into x squared plus 2 plus h, subtracted x squared, divided everything by h, and simplified to 2x plus h. Then he took the limit as h approached 0, leaving to x. He circled it. This, he said quietly, is the slope of the tangent line at any point on this curve. Students leaned forward. The abstract symbols now described something visual and real. The steepness of a hill, the speed of a car, the growth of a population. He told them calculus was not invented in a single flash of genius, but developed through the work of thinkers who wanted to measure the world precisely. Problems of planetary motion, falling objects, and changing rates demanded new tools. The derivative became that tool. Harper then connected it to physics, explaining how velocity is the derivative of position, and acceleration is the derivative of velocity. Layers of meaning began stacking together. He worked through another example, finding the derivative of 3/5x plus 7, applying the power rule to get 9/5. He explained why constants disappear and why exponents drop by 1. Each step built confidence. As they are moved forward, Harper shifted to integrals. He shaded the area under a curve and described accumulation. How tiny rectangles added together could approximate space beneath a function. He introduced the fundamental theorem of calculus, explaining that differentiation and integration are connected, almost like opposites in balance. When he evaluated the integral of 2x from 0 to 3, arriving at 9, he showed that the area could be found through antiderivatives rather than endless summation. A quiet realization spread across the room. Calculus was not a collection of tricks. It was a language describing change and accumulation, motion and growth, limits and certainty emerging from uncertainty. By the end of class, the fear many students carried had softened into curiosity. Harper placed the chalk down and reminded them that confusion is part of learning. That every expert once stared at symbols that made no sense as they packed their bags. Several lingered to ask questions, no longer intimidated but engaged. In that lecture hall, calculus stopped being an abstract requirement and became a way of seeing the world, structured, logical, and unexpectedly beautiful.